I finished assembling the Eggtimer EZ-DD altimeter. So by assembly, I mean it comes as a blank board except for this pressure sensor, which is a tiny component, is pre-soldered on. Everything's through hole except for this regulator. And the instructions are super well written. So if you soldered things before, just follow the instructions and I think you'll have no trouble at all. One thing that I found is I use a magnifier to be able to do it, even though these are pretty big parts compared to some of the normal stuff. But I also found that I had a jeweler's loop that's 30x power, and this turned out to be really useful for me. Some of the part markings are really difficult to see even under 5x magnification. So having this and being able to inspect some of the solder joints to make sure they look good really helped. So I took my time and it took me about 2 hours to assemble everything. And there's a handful of tests built into the assembly instructions that you can follow. The final test, in the instructions, it uses a vacuum cleaner. And there's a YouTube video on that that's linked in there. But I'm going to do something a little bit different today. But I have set it up in the same way. So an incandescent lamp that's hooked to what would be the apogee E-match. And then an incandescent lamp that's hooked to the main. The battery's right in the bottom, and I just put that rubber band there to hold everything together. So what I'm going to do is I'm going to put it in a syringe and use that to do the test instead of the vacuum. And I bought this 550cc syringe, and unfortunately it just doesn't fit on here. Oh, one thing I wanted to mention too is I had a hard time finding the incandescent lamps. It turns out all the stuff I have, even though I thought it was pretty old, was LED and it looked incandescent. I did find this set at Hobby Lobby in the floral department. So it's June, they didn't have the Christmas stuff out, but there was an incandescent set in there. So that's where I got these bulbs from. So I'm gonna go ahead and turn it on. And it starts to beep out some codes. I also have a Perfect Flight Firefly that I'm gonna use mostly just to check my my operation here. So I'm gonna just kind of pop that on top under the rubber band as well to hold it in position and stuff everything into the syringe. And then I'm gonna put the plunger in. I'm gonna put it to 450. Try to get it pretty much exactly. Okay, it's a lot fainter now, but now the EZ-DD altimeter is doing a really fast chirp. That's ready. It's gone through all its diagnostics and it's ready. The Firefly similarly gives you about 30 seconds to assemble the rocket. The Firefly is just an altimeter. It doesn't really control. And then it does the fast blink. So now both of them are ready. And this would be, okay, I'm carrying them to the pad. Actually, you wouldn't have it armed yet in the case of the EZ-DD, but they're basically on the pad, ready to go. So both altimeters are trying to sense a launch event. And let's talk about that a little bit. So I'll explain my rationale. So the way these work is they're both based on air pressure, and so if you remember the gas equation, pressure times volume equals a couple of constants times the temperature. The constants depend on the amount and type of gas. And you can, for a given gas, you can say, hey, the pressure times the volume over the temperature is a constant. And further, if you want to look at some different scenarios with a specific gas and a fixed amount, then you can have this relationship here. And in this case, what we're doing is we're just going to ignore temperature and assume it's constant for all our experiments. And so what we end up with is whatever the pressure volume relationship multiplied together is going to equal any different pressure volume relationship. And the way these work and the way they sense altitude is that because there's basically less air on top of you, as you go up in altitude, the pressure decreases. And it decreases by 1.2 kilopascals for every 100 meters that you change in terms of altitude. And that also works out to 3.66 kilopascals for every 1,000 feet. So we're going to work in feet for this experiment. The current atmospheric pressure here is 1,012 millibars, which is really just 101 kilopascals. So typically the weather gets reported in millibars instead of kilopascals. And so the question I want to answer is, if I increase the volume in the syringe from 450 cc's, which is what we just set it to 500 cc's, I just picked those numbers randomly to give me a little bit of a 10% difference basically, and something I could look at and see pretty easily when I did the experiment. But I want to know, it simulates what change in altitude, right? So what I do is then I go through and I say, look, the original pressure, P1, was whatever the atmospheric pressure is here, 101 kilopascals. There's 450 cc's in the syringe. And then after I pull it to 500 cc's, I want to know what the resulting pressure will be. Well, if you just do the math on that, you can solve for P2, and it's 91 kilopascals, which makes sense, right? We increased the volume, so the pressure dropped. And the delta in pressure, which is really what I'm interested in, is the 91.1 minus the original pressure, starting pressure, and so it's minus 10 kilopascals. So now to find the height, I just used the relationship we talked about a second ago, which is 3.66 kilopascals for every 1,000 feet. I made it negative because we're simulating going up. So then I set that equal to my 10.21 delta height. Again, just cross multiply and solve for my delta height, and I get 2765 feet. So basically, pulling the syringe from 450 to 500 simulates, hopefully, the amount of pressure change a rocket would see when it went from whatever its launch altitude is to 2765 feet. The other one that I wanted to calculate was how many cc's, how many cubic centimeters would I need to change to simulate a 600 foot altitude change. And the reason for that is the EZ-DD, what it does is it detects the apogee, fires the apogee charge that separates the rocket, then it falls, and when it detects that it's 600 feet back above the original ground level, then it fires the main. And so for that, we kind of do the same thing, but in reverse. We're going from height to pressure instead of from pressure to height. So the delta pressure, again, delta height, using that same equation, and then solving for the fact that we have 600 feet. What is my delta pressure for 600 feet? It's 2.19 kilopascals. And so then I use the same relationship we had before, P1, V1, P2, V2, and here's my original at my 450. Then here's my new pressure, right, that simulates the 600 feet rise. So I subtract the 2.196 I have here, and that'll tell me the volume that's required. And so again, just kind of doing algebra to solve that, I get a volume of 466 cc's. So that's the supporting calculations. Let's give it a whirl. All right, so again, the EZ-DD is chirping away. The Firefly is blinking. I'm going to cover up the end of it and do my best to pull it smoothly right to 500, and then I'm going to go back down. So that mimics the rocket going up and floating back down. What you'll hear is as soon as both of them detect the pressure drop, they're going to go quiet because that's the launch condition. You must stop at the 500, and you see that the light fired there. That would be the apogee charge firing from the EZ-DD. And so the rocket would be separated and falling back down. So I'm going to let the pressure go back down. And when it hits 460, so then the main fires. I'm back to 450, I release it, and I'm done. And now both altimeters will detect that, hey, we're done, and they're going to beep and flash out the altitude.